In the last 2 months or so, I saw quite a lot of discussions about pros and cons of various power supplies to power a DCC layout. Many arguments were quite interesting and helpful, and others flat out wrong or even dangerous. And with my DCC booster becoming available soon, I thought I would add my own points of view to the mix and use this video to cover some do's and don'ts of powering a DCC layout. Hello everyone and welcome to the IoTT channel. I am Hans Tanner. Welcome to all new subscribers and welcome back to everyone else. I am happy you made it here and thank you for your support of my channel. Here are the 3 power supply topics I will discuss today. First, safety. When working with power supplies, we are only a small distance away from potentially lethal voltages and we are dealing with significant power and energy levels, so care needs to be taken. Unfortunately, hobbyists are too often too relaxed about the dangers inherited with power supplies, so I make this today's first topic. Second, performance parameters, mainly amperage and voltage levels and how to deal with it. How to make sure your locomotives get the power they need to operate and how to prevent the layout from catching fire in case of an overload or short circuit situation. And third, grounding principles. This is a topic that I have not seen a lot of discussion about, but incorrect grounding in many cases can be the reason for communication and control problems on the layout bus caused by ground loops and, if not done properly, can even cause harm to connected equipment like computer USB ports and the like. Lots of stuff to cover, so let's get started. As you might know from other videos, I started my professional career with an apprenticeship as electrician. Over the course of 4 years, I systematically learned all the activities related to bringing electricity to the places where people needed to power their devices. And an important part of that was, of course, learning all the rules and regulations to ensure that no one gets electrocuted. One of the more drastic textbooks we used had a lot of illustrations about what can go wrong. Pictures of burnt down houses and dead people who tried to reach for a hairdryer while sitting in a bathtub and the like. One picture was particularly brutal and it still is stuck in my memory. It was from a model train room and since I was in that hobby as well, it immediately caught my attention. The owner of the layout wanted to make everything look clean and did not like the idea that the power cable stuck out from the front of the layout. So what he did is installing an electrical outlet on the front side instead of the cable with a plug, and then used a few feet of cable with 2 male connectors to bridge between the wall outlet and the outlet on the layout to power up the transformers that were installed underneath the layout framework. Very aesthetic and of course it worked well, so problem solved. And safe as long as you always first connect the layout side and then the wall outlet. Unfortunately, sometime later in an unattended moment, his toddler granddaughter crawled up to the layout, somehow managed to pull the plug and did what toddlers do when being on a discovery trip, stick it in the mouth and suck on it. It sounds like a miracle, but somehow she survived. The picture in the book that I still cannot forget showed a little girl's face with a good part of the mouth and nose missing and significant burning wounds all over the face. Trust me, you don't want to be the grandfather who is responsible for countless trips of the granddaughter to cosmetic surgery and without any real chance to ever fully restore the looks nor the functionality of missing or burned up nerves for smell and taste and speech and the like. Here are a few core rules to make sure this cannot happen to you. First, If your power supply is designed to use a ground wire, use it. Ground wires are typically used to connect enclosure parts made from metal back to Mother Earth, so that in case anything becomes loose inside the device and a hot wire touches the enclosure, it creates a short circuit and the line breaker can take care of it. The connection to Mother Earth is done using the third contact on the electrical outlet. If your outlet only has two contacts, as it is still found in older buildings, have a grounded outlet installed by a professional, or do not use power supplies that require a connection with an earth contact. Never ever think about just cutting the ground contact from the connector and use a 3-wire cable on a 2-pole outlet. This will disconnect the safety ground from the enclosure of your power supply, and if anything goes wrong, you may get electrocuted when you touch it. Second, make sure that no metallic parts that may carry line voltage can be touched accidentally or even intentionally, for example with a screwdriver or a piece of wire. I want to point out specifically the many cheap power supplies that you now can buy from Amazon or AliExpress and look something like this. A metal case with some screw terminals with a plexiglass strip on top to prevent from touching the terminals. I use them myself and I like them a lot because of the performance characteristics, but using them without an additional enclosure is not a good idea. Much better is to put them into a sturdy plastic enclosure, create some small holes for ventilation and screw the power supply to the enclosure. Or create a 3D printed frame the size of the enclosure to hold it in place and prevent it from moving around. Never ever install them without additional protection just somewhere under your layout. If a wire comes loose, it can create a short circuit or cause a fire, or you or your granddaughter can get electrocuted. And third, make sure it stays that way even if somebody pulls on the cable or the power supply falls down from the layout. Or it falls down and somebody grabs the cable to prevent it from hitting the ground hard. In other words, always use an enclosure that can take some serious hits, is firmly closed with screws that cannot just break out, and there is a good strain relief mechanism on the cable. If you lift up the power supply on the cable, all force should flow into the enclosure and none should reach the contact terminals, even if the force is a multiple of just the weight because you catch it in free fall. Some enclosures do have a built-in strain relief to make it easy. If yours does not, it is easy to make a 3D printed part to conduct the cable through and secure it with a cable tie. Search on Tinkercad for cable strain relief and you will find many different designs for that purpose. In addition, make sure you are not using metallic screws through the wall of the enclosure, as this would create a potentially power-carrying metallic contact point touchable from the outside. If you observe these 3 simple rules, your power supply should be safe and not cause any harm to anybody. The second important topic to discuss are the performance characteristics of your power supply, mainly voltage and available current output. This is an area where there is quite some difference between traditional analog model railroads that control the locomotive speed by changing the track voltage, and DCC systems where the track voltage is always the same and the speed change results in a different current flow. In this discussion, I am only covering DCC systems, so if you are running analog locomotives, I'm sorry, what I'm saying is not applicable for your layout. The first thing to check is whether your command station requires DC or AC as power input. Why might this be important? Well, this becomes obvious if we compare typical power input circuits of AC and DC command stations as shown in these schematics. The first picture shows the power input of a command station or booster that is designed for DC input. The negative pole of the input goes straight to the system ground. The positive pole, on the other hand, may run through a reverse polarity protection diode and then provide the positive voltage to the H-bridge, which generates the track output. In order to make things work, you need to apply a DC voltage using the correct polarity. If the voltage is reversed, it does not work, but no harm is done as long as there is a reverse voltage protection diode in place. Some systems may have no reverse polarity protection. For example, if you build a DCC-X command station with a standard motor shield. In this case, you need to be extra careful to get the polarity right, or you may damage the mother shield board. The second picture shows a typical command station or booster designed for AC input. Here, the input is run through a bridge rectifier to create DC, which then is fed into the H-bridge to generate the DCC signal. The typical example for this are the Digitrax command stations and boosters. Looking at the schematics, it becomes clear that you can supply this circuit either with AC or with DC. And in fact, in some cases, Digitrax recommends using a regulated DC power supply as input, for example, for the DB200 plus 8 amp booster. So, if your command station requires DC, for example, a DCC-X command station equipped with motor shield or power shield, you need to use a DC power supply and make sure you get the polarity right. If your command station is built for AC input, you may use a standard AC transformer or a DC power supply, and in this case, the polarity does not matter as it runs through the rectifier anyway. The next question is, what current rating should your power supply have? The simple answer is, the more the better. In any case, the current rating of the power supply should be higher than the current rating of the booster or command station, and then some. If your booster or command station is built for 5 amps track power, you should choose a power supply that can continuously deliver 6 or 7 amps. If you choose a power supply with too little amp output, it may reduce the voltage or power down before the protection functions of the booster or command station are activated, which may lead to all kinds of problems. This is particularly true in case you drive 2 or more boosters from one single power supply, which you can do. But also here you should make sure that the current rating of the power supply is sufficient to cover all connected boosters when they are operating at nominal load, plus some reserve. Digitrax gives a nice example on the DB200 Plus webpage. To power this 8 amp booster, they recommend the 20 amp regulated power supply and state that one power supply can be used to power 2 DB200 Plus boosters. So it is 20 amps supply rating for a total of 16 amps booster current. This ensures that one booster can have an overload condition and shut down, but it does not impact the function of the other, and that is what you want. An error somewhere on the layout should be contained to the track section where it occurs and not impact other power districts on the layout. The second current-related characteristic that is important is the momentary short-circuit current. This is the current pulse the power supply can deliver for a short period of time before the internal protection is activated. The rule of thumb is it should be significantly higher than the nominal current rating of the connected boosters and command stations so that they can properly detect a short circuit and shut down. If the power supply limits the short circuit current, it is not possible for a command station or booster to distinguish between heavy load and an error condition, and the built-in protection may not properly work. For example, you have a command station with a trip current set to 5 amps and you run some heavy trains with a total consumption of say 4.8 or 4.9 amps, and your 5 amp power supply is near the maximum output. Needless to say, by the way, that pretty much everything gets quite warm at this point, but let's assume it works. Now, one of the trains derails and creates a short circuit. If this happens, your power supply should be capable of delivering an extra current pulse of at least a half an amp above the nominal current for a few milliseconds, so that the booster can clearly detect the trip current overrun and shut down the track. If the power supply is too weak or activates an internal protection function instead, the command station might stay in regular operation mode with current flowing through the shorted track. Now, in reality, you will rarely be able to load a booster or command station up to the nominal current. The reason is that the current consumption of a locomotive is not continuous, but generates current spikes as seen in this oscilloscope screenshot. It shows the current consumption of an HO locomotive with a Digitrax DH84 decoder at speed step 5 of 100. We see that the motor is pulsed with a frequency of about 60 Hz. This is the reason for the typical hum you hear at low speeds. If you look at the current consumption from a power supply point of view, at this low speed the locomotive will draw somewhere around 200 to 300 milliamps. But if you look at the individual spikes, they might well be around 1500 to 2000 milliamps, but only for a short moment. Now, if we increase the speed, the pulses get longer, as seen here, and while the overall current consumption of the power supply is also going up, the peak values of the individual pulses tend to become lower. And at full speed, the motor is constantly on, and the peak current and the supply current are basically identical. What that means is, if your booster is loaded to say 4 out of 5 amps, one additional locomotive, even at very low speed settings, can generate a current spike that makes the booster shut down because the trip current is reached during the pulse. Or the other way around, if your booster trip current is set to 5 amps, it will be pretty hard to load it with a continuous current of say more than about 4 amps, because some spikes will likely trigger the trip current and the booster will shut down temporarily. So, with all that in mind, what power supplies are suited best for a DCC layout and what would I recommend? And once installed, is there a good way to test the proper functioning of the power supply and the protection functions? In my experience, it is best to use a regulated power supply with a nominal output current higher than the current ratings of the connected booster or command station. Good examples for smaller layouts are old notebook power supplies. They typically have a nominal current of around 5 amps and a voltage around 16 to 20 volts. For more current, I prefer regulated power supplies as the one shown before with the metal housing, either with a fixed output voltage or even adjustable, and placed in an appropriate enclosure to make it safe. The main advantage of the regulated power supplies is that thanks to the quite big internal capacitors, they typically can provide a brief, short circuit current pulse that is significantly higher than the nominal output, even if they are operated under nominal load. As discussed before, this is a precondition for reliable short circuit protection. And here is a simple way how you can test your setup. Power up your track and then place an ohmic load on it that draws about 80 to 90% of the nominal output of your booster or command station. You can use a power resistor or an incandescent lamp, for example an automotive headlight bulb. The effect of an ohmic load is that it generates a load that is not pulsed and therefore is the same for the power supply. Here is how an ohmic load looks like on the oscilloscope. So if your booster is rated for 5 amps, load it with about 4 amps for the test. Don't be surprised, the booster will typically warm up under this load. Let it run for a few seconds and then create a short circuit on the track. If everything works, your booster or command station will shut down immediately, while there is no effect on the power supply side. If you have a second booster connected to the same power supply, it should keep running as normal. If that's the case, it means that the power supply was capable to provide enough extra current so that the short circuit was reliably detected, and you have implemented a selective protection of your power districts. One question that comes up frequently is how to adjust the voltage of the power supply to the desired track voltage. You are, for example, using a Dell notebook power supply which typically has a 19-volt output, and you want to power an HO layout with the recommended 16 volts, so you need to reduce the voltage. Some people have suggested to use a DC-DC converter for that purpose. The problem with that approach is that all DC-DC converters I have tested so far pretty much limit the short circuit current, as their internal protection function works quite fast. As a result, the DC-DC converter shuts down, or even worse, reduces the output voltage before the command station detects a short circuit, and current might flow through the shorted part for a longer period of time. The better solution, in my opinion, is using one or more diodes in series. For example, power diodes like these 6-amp types, which are available for about 20 to 30 cents a piece. They typically have a forward voltage of about 0.5 or 0.6 volts, so you can put some in series to reduce the voltage to the desired level. You can even put 2 strings of diodes in parallel to be on the safe side with the maximum current. The last topic I want to talk about in this video is grounding, which is not covered very often, but is quite important when using a command station and one or several boosters and other devices. In principle, it's simple. A ground wire connects to the ground contacts of each device to make sure that all devices use the same electrical potential. This can be illustrated with the simple Arduino stack of a DCC-X command station. The minus pole of the power supply is used as ground and is distributed to all stacked boards using some pins of the pin header. As a result, ground of the Arduino board is the same ground like the one on the motor shield or the Wi-Fi shield or whatever board is connected. And as a result, if you supply the individual boards with different power supplies, the voltages are in reference to each other. If you supply the Arduino board with 5 volts and the motor shield with 12 volts from a different power supply, you can measure 7 volts between the 2 plus poles because the ground connection provides a shared level to measure against. The same is the case when using several separate devices, for example a command station and a booster. In this case, we need to run a wire from the command station ground to the booster ground to make sure that the track voltages provided by each device are in reference to each other. This ensures, for example, that the locomotive can cross from one power district to the next without problems, or it makes it possible to use an auto-reverser to change the polarity in a reversing loop. So, if you have several devices, you should run a wire between them and connect the ground contacts of each device to it. On Arduino-based devices, that would be the ground pin or the negative pole of the power plug, which is the same. On commercial devices, you typically find a ground terminal somewhere. Connect all these points together and then connect one point of the ground wire to a defined ground potential, for example, an enclosure of a device that is properly grounded. If you use a power supply with an earth wire, it is also a good idea to measure the resistance between the earth pin of the line connector and the minus pole of the DC outlet. I went through some of mine and found 3 different versions. I have some that have a firm connection between the negative DC pole and ground. Then I have some that have an infinite resistance, meaning the output voltage is floating and can assume any potential in reference to Earth. And then I found some that have a 1K resistance between the Earth pin and the negative DC output, so sort of a loose coupling. I was not able to clearly establish rules who is using what, but it seems that my Dell power supplies have a grounded negative output, while the ones from HP are floating. But then there are exceptions, so it's best to check for yourself. The rule for grounding is this: if there is a zero resistance between the Earth pin and the negative DC output, you can use this as ground reference and there is no need to run the ground wire to another Earth connection. If you can measure a resistance greater than zero, the output is at least somewhat floating and you should connect your ground wire to a proper Earth point. And if you use several power supplies and at least one has a grounded negative DC pole, you are good, as well as one Earth connection will take care of the entire setup. In case you are using a DC power supply on a command station designed for AC input, you must always connect a ground wire to the ground pin of the command station. The reason is that your negative pole from the DC supply runs through the bridge rectifier, which will create a 0.7 volt difference between the DC supply ground and the system ground, which is not good. Connecting the system ground to Earth bridges the rectifier and makes sure your system ground really is at zero. And finally, the whole grounding topic may become a non-issue if you have your components connected by a communication bus such as Loconet. In that case, the Loconet cable carries two ground wires which provide common ground to all connected devices. The only thing that remains to be done is making an Earth connection somewhere in the network. Usually this is done right at the command station. If you're a tinkerer and like to build your own devices, then there is an additional ground-related topic you should be aware of, so-called ground loops. This happens if the ground of two devices is at different potential and when they are connected via ground, a current is flowing. If one of the devices is a USB port of a computer, it is even possible that it gets damaged. How can this happen? Well, let me show you. Here is the schematics of a command station with the microcontroller and the H-bridge that generates the DCC track signal. As discussed before, the system ground is connected to Earth and therefore is at 0 volt. Let's assume that VCC is 15 volts to make things simple. Furthermore, let's assume the H-bridge is an L298 bipolar type, as it is used on the standard motor shield. It has a source and sink saturation voltage of 1.5 volts. This is the voltage loss over the transistor when it is conducting as shown in the L298 datasheet. As you see, it depends on the current and can be quite significant. As a result, the DCC voltage at the output of the command station is at 13.5 volts at high and at 1.5 volt at low in reference to ground, and peak to peak it is 12 volts. Now let's assume you use an Arduino to build a switch decoder. To make things simple, you just connect the DCC to provide power and information to the decoder. For power, you run the track input through a bridge rectifier. The forward voltage of the rectifier diodes are the typical 0.7 volts, so your resulting DC voltage from a 12 volt track input is going to be 10.6 volts. And with reference to the original Earth potential, your positive voltage is at 12.8 volts and the negative voltage, which you would like to use as system ground for your decoder, is at 2.2 volts. The question is, can this new system ground provide a current when connected to the original ground? The answer is yes. So Now, let's assume you need to debug your device and therefore connect it to a computer that is grounded to earth potential. What you basically do is creating a short circuit between your 2.2 volt ground and the 0 volt earth ground, and since the 2.2 volt ground is capable to deliver current, you have created a ground loop. To avoid damage to your computer, you should either use a USB port isolator, which always is a good idea when playing with DCC devices, or use a computer that runs on battery or on a power supply with floating output. A real-world example for what I just described is the quite popular booster design from Dave Bodnar. If you study the schematics carefully, you see that the optocoupler does not provide real galvanic separation, and the DCC rectifier leads to an elevated ground level as I just described. Therefore, connecting the Arduino to an USB port with earth ground potentially creates a ground loop and should be avoided. Another real-world example is the original Digitrax DS54 switch decoder. This device used the bridge rectifier to generate the supply voltage, which resulted in different ground levels for the decoder ground and the ground provided by the Loconet connection, so the very same ground loop problem I just described. Digitrax kind of solved the problem by connecting the two different grounds via a 1K resistor, allowing for some current to flow, but at the same time limiting it to a few milliamps. This worked as long as there were only relatively few devices connected to the same Loconet, so that the overall resulting current in the Loconet ground wire was still small. In later designs, as you are probably aware if you are a Digitrax user, they did no longer power the devices from DCC, but used separate power supplies for each device, which of course eliminated the ground loop problem once forever. And that's it for this video. I hope this information was useful or at least interesting for you, and you are not more confused than before. I am aware that the topic is a bit technical, but I tried to condense it to a few simple and applicable rules that allow you to power your layout safely and reliably. If you like this kind of information, please click the like button below or write a comment in the comment section of this video. Also, to see more videos like this, subscribe to the channel and hit the bell icon so that you are in a premium seat when new videos come out. Thanks for watching and see you in the next video.